The night sky seems unchanging, with constellations that appear to us almost as they did to the ancient Greeks. But the more we study the night sky, the more we discover that dramatic changes are taking place. The most spectacular events on the sky are cosmic explosions, supernovae, and gamma-ray bursts.
The origin of the constellations is lost in antiquity. They are described both by the ancient Greeks and the Jews. This is because stars like the Sun shine for billions of years without major changes in brightness. Stars are usually stable systems in what is called a state of equilibrium. One can compare it with a bicycle pump. If you put a finger on the valve and try to push the plunger all the way down, it soon becomes clear that you cannot. The pressure of the air in the pump is too strong, and you can only push the plunger to a certain point where there's an equilibrium between the pressure in the air and the force from the arm. In stars, there's a similar balance between the force of gravity that tries to contract the star and the pressure that counteracts the contraction. This is a very stable equilibrium, and this is why stars can change very little even over billions of years. But where does the pressure come from?
The origin of the pressure is the very large temperatures inside the stars. Nuclear reactions take place in the stellar cores. In the nuclear reactions, smaller nuclei combine to form larger nuclei, releasing energy, heat. This heat is the cause of the pressure that prevents the star from collapsing under its own weight. But when there is no more fuel remaining in the core of the star, then the equilibrium is broken and the star dies. The death stars can give rise to a multitude of cosmic fireworks, depending on the mass of the dying star. Stars weighing up to 8 times as much as the Sun die relatively peacefully. The outer parts of the stars are cast relatively slowly out into space, while the remainder, the star's hot core, is exposed as what we call a white dwarf. A dense sphere the size of the Earth, but with a mass close to the Sun. Heavier stars face a much more violent death. Even though they have much more fuel, they have a much shorter lifespan than stars like the Sun. Massive stars burn through much faster. Stars 10 times as heavy as the Sun only live approximately 10 million years, that is 1,000 times shorter than the Sun. When such a massive star dies, it flings out the outer parts with colossal speed, many thousands of kilometers per second. The star lights up tremendously, sometimes briefly as much as an entire galaxy. We call this a supernova. The core of the star collapses into extreme density, either into a so-called neutron star or a black hole. Neutron stars and black holes are very small, only a few kilometers wide, but weigh around the same as the Sun. Hard to imagine.
It may appear strange that a collapse gives rise to an explosion, and we only know parts of the explanation. In the collapse itself, so-called gravitational potential energy is released. If I let a stone fall to the ground, it will accelerate, i.e. increase its speed more and more until it hits the ground and releases its kinetic energy. In the same way, the collapse of the star gives rise to the release of an enormous amount of gravitational potential energy, which is converted into heat and results in an explosion. Furthermore, radioactive nuclei are formed in the final seconds of the star's life, which is critical for how bright the supernova becomes. Finally, at the end of the star's collapse, a strong wind of neutrinos is formed, which is believed to amplify the explosion.
There are good reasons to be interested in supernovae, because they are crucial for the formation and diffusion of elements like oxygen, carbon, silicon, and many elements that we and the Earth are made of. The intensity of supernova explosions is crucial for dispersing the chemical elements formed during the lifetime of massive stars into the surrounding gas clouds, where new generations of stars and planets form. Many supernovae have been discovered through the ages, including one observed by the Danish nobleman Tycho Brahe, who in 1572 discovered a supernova in the constellation of Cassiopeia. The latest discovered with the naked eye was a supernova observed in 1987 in our neighboring galaxy, the Large Magellanic Cloud. From this supernova, we also detected neutrinos, so we know exactly when the supernova exploded, on the 24th of February at 6:35 in the morning in 1987. Or rather, that is when the light reached us. The explosion really took place 160,000 years earlier. The supernova was observed for several years after the explosion, and its expanding remnant is still being studied in great detail because it is so close to us.
It is clear that we cannot base a study of supernova on the incredibly rare incidents that can be seen with the naked eye. Therefore, we now use powerful telescopes to search large parts of the sky for new supernova. The first to start this type of search was the astronomer Fritz Zwicky. In September 1936, he discovered the first supernova identified in this systematic way. Nowadays, both telescope and detector technology are much better than in Zwicky's time. So now, hundreds of new supernovae are found each year. But violent supernovae are not the only cosmic explosions. There are also gamma ray bursts. Gamma ray bursts are powerful bursts of gamma rays, lasting from a fraction of a second to several minutes, in very rare cases up to half an hour. Gamma radiation is in principle the same as visible light, that is to say photons. But gamma ray photons are much more energetic than visible photons. Each gamma photon has approximately 1,000,000 times more energy than the photons we can see with the human eye. When gamma ray bursts were discovered in the 60s, their origin was a complete mystery. Today we know that gamma ray bursts are formed in very rare extreme supernova explosions.
If the dying star is very heavy and has a core that spins very rapidly, then a black hole with a surrounding disk of infalling matter can be formed. Theoretically, it is expected that a jet of matter will be launched perpendicular to this disk with extreme speed, very close to the speed of light. Gamma ray bursts are believed to form in these so-called relativistic jets of matter. If the jet happens to point towards Earth, then we see a gamma ray burst.
In our research, we currently use gamma ray bursts as a kind of glowworm that lights up and tells us where to look to study the earliest stages of extreme supernova, or to locate the galaxies that form the short-lived massive stars. Because gamma ray bursts are so powerful, we can see them out to the largest distances, and hence to the earliest times of the universe. In fact, the most distant object we know today is a galaxy that formed a star that died and created a gamma ray burst more than 13 billion years ago, and which we observed on the 23rd of April 2009. By studying the light from this and other of the most distant gamma ray bursts, we can study the conditions in the universe when the very first stars and galaxies formed a few hundred million years after what we call the Big Bang.